Hello, today we are gonna build a machine learning project from scratch. In this project we will be predicting Mercedes sales. So without further ado, let's make the history. In the beginning I will explain you what you need to make this project. There will be a link to this dataset in the bio, just download it and open it in your editing software. Before we start to code, in this CSV file with your data, there are three columns. First is age of the customers, second is their estimated salary, and the third one is our output variable. It is if the customer bought a car or not. This data will serve us as a training data. After we train a model on this data, we can predict any future customers. Let's move to the code. The first library, I will import NumPy SMP as always. NumPy is used for numerical calculations to make it easier. And the second, I will import pandas and SPD to make easier work with our data frames. In our case, it is the car purchases.csv file. So we have the data, we need to load it somewhere. So I will define a variable called dataset and I will use pd pandas function pd.read csv, and here I will put the name of our file for car purchases.csv. Now we have loaded this data into variable called dataset, and I will divide this data into two groups, into X and Y. The X will be the input features and Y will be our result we want to predict. So X is equal to dataset.ilog, integer location, all the rows and all the columns excluding the last one, and I need values from there. Y, this will be the big X, not the small one, capital X, yeah. Y will be also the dataset, integer location, all the rows and only the last column, and I need the values from there. Yeah, like this. Now let me check if everything is working. I will print the X dataset, and there is a mistake. You cannot call this. It is written without parentheses. Now I save the code and run it again, and as you can see, this is our input dataset with all the features, and we found the labels. After splitting the data into input, features and the result, that's not all. We need to split this data also to training and test set to make our model more accurate and test if it's working fine or not. As I mentioned, I will import another library. It is called sklearn. So from sklearn, let me close this. I will import method called train-to-split. What it does, it splits the data into training and test sets. Yeah, simple as that. So it has the syntax as xtrain, xtest, ytrain and ytest, and I will use the train test split. The first parameter is input feature, the second is dependent variable, and I will use some more not mandatory parameters. The first one is test size. I will use 0.25. That means the 25% will be allocated into the test set and 75% allocated into the training set. The next will be the random state, not like this, but like random state is equal to 0. This will help with reproducibility of the code. That means that I will have the same result every time when I run the code, and also you will have the same result as me. Now I can print out, for example, the y test shape, and also I will do this y train dot shape and the y shape, and you will see that it is split between those two. What is wrong again? Yeah, there is another mistake. I cannot import train test split from sklearn because it is like in another module of sklearn. So I need to import train test split from the model selection of the sklearn. Okay, everyone do a mistake, so don't worry. Run the code. As you can see, the shape of y test is 25 rows and 1 column. The shape of y train is 74 rows and 1 column, and together it gives us the number 99, and as you can see, everything is correct. For classification of our data, we will be using SVM, the support vector machines. Let me play a quick intro to SVM for you, and I will be back right after it.
In machine learning, the fundamental challenge involves taking a bunch of objects and categorize them into two or more distinct groups. Is this picture of a horse or is it a car? The SVM support vector machines are one of the most simplest and the most elegant way of classification. Each object you want to classify is represented as a point in the n-dimensional space, and the coordinates of this point are usually called features. SVM perform classification by dividing the objects into separated areas. These areas are separated by line in 2D and plane in 3D. Both of them are called hyperplane. The main concept of this algorithm is to find the best fitting hyperplane that have the biggest margin from all the separated groups. The points that determine the edges of the margin are called supporting vectors.
So now you have a basic idea what SVM is. Let's move on to the programming of the SVM class. We will do the SVM class from the scratch, so with all the mathematical details. If you want less mathematical video, watch the last SVM video. It just use all the built-in function from sklearn to make this classification. But in this tutorial, you will learn much more than in the previous one. Let's go. Class SVM classifier. In this class, I will define all the methods used for the SVM classification, and in every class in Python, the first function, which is called method in object-oriented programming inside the class, I will define the constructor that initialize our class features, or otherwise called properties. There will be define init like this. Self, the class is like a blueprint for an object. Imagine you have a blueprint for a house, but you can build 10 houses from the blueprint. And that house that is built from the blueprint will be called object of the class or one instance. It's up to you how will you call it. So this init method is mandatory. In this method, I will define 3 attributes for our class: the learning rate, number of iterations, and lambda parameter. If you wanna assign these properties to the objects, you need to write it like this: self, that object, learning rate will be equal to the learning rate, yeah, like this. And the object number iterations will be also the number of iterations. The learning rate is the impact of one iteration on our model, and the number of iteration is number of iteration. And the lambda parameter, there is a special parameter that will help us to make a balance between overfitting and underfitting the model and find the best fitting line that will not only divide our training and test set, but will generalize on future data from the real world. So as in the previous features, the self.lambda parameter is equal its lambda parameter. If we won't use this lambda parameter, our model will perform like this. It will fit the line that will match every point. We don't want that because it won't generalize on the new point. And also, we do not want to, but we also don't want to put a big value into our lambda parameter because it will underfit the training set, and then it will only decide on the last values like this, and it won't generalize on the real world data. It will perform even worse than the overfitting one. So the lambda parameter will help us do this in the middle, the optimum line. I cannot test this right now because it won't do anything. Need to wait to the end. The second function will be the fit function. The fit in the machine learning means that it will learn on the data. The fitting is like training the model. Yeah, so here I will put our data, so the y and x, and also the self. In this training function, we'll be using this equation of a hyperplane. That's the line or the plane that is dividing the classes, two classes or more. In our case, two classes, only two. And it has equation of y is equal to w times x minus b. The b is the intercept or the bias where to go, and the y is our prediction. It is like a equation of a simple line, but there is one difference. The w is not slope, but it's a weight vector. It can have more than one number. If our x will have 4 input features, it will have 4 dimensions, so the weight vector will also have 4 directions, and it will somehow sum up together, and it will create one line or plane. And b will be always the bias where to move on to which side. This class doesn't know how our data look like, so we need to define some interface that will get the resolution of our input dataset. So self.m and self.n will be x train shape. That means the m is number of rows and n is number of columns. Now we have the resolution of our dataset, and we need to define the weight vector, the w, and B. The W and B are model parameters that will be changing every iteration, and this will help us to predict new values. After thousands of iterations, W and B will have some value. We will put there the X, the input feature, and we will got the result. Like this. Put X, W and B will be trained, and we will got the result. Yeah? So we need to define the starting point of weight vector and the bias. Self that I will put here white row. Self.weight will be equal to, in this weight vector there will be that many parameters as are columns in our input data. So it will be numpy array, and it will have same number of columns as our input data. The bias will be 0 in the beginning. Also, we need to put the data into this class, because this class doesn't know where is the data. We need to put there into the object. So self.x is equal to x and self.y is equal to y. Now we will define a function that will make the iterations, and it will learn slowly, iteration by iteration. It will tweak the parameters to make the prediction more accurate. For e in range, you need to that object iterations, so self number of iterations like this. And for the number of iteration, we will update. We will use another method we will define in a few seconds. Self that update weights. I do a lot of mistakes today. In the method of a class, we need to put self as the first parameter. Now it is fine. In updates weight function, we will be updating the weights, and that means we will be moving this line, the hyperplane that is dividing the classes. And it will divide the classes, there will be some equations, and it will give some values, but in the end, the value of one class, the result will be always 1, and other class will be minus. And the bias, the plus bias will be moving to the positive class, and minus bias will be moving to the negative class. Let's code the update weight function. In update weights, we will be updating the weights, and there is a difficult math behind it. I will provide a link in the description. I will define our predicted y is equal to numpy, where if the self y is less or equal to 1, it will be minus 1, or otherwise it will be 1. As you saw in the picture, our two classes will be the minus, the negative class, and the positive class. Next thing is condition. It is from the hinge loss function, and it is deciding if the point is classified correctly or not, and it will move the line or update our hyperparameters depending on the result. And it is the same of our equation for the hyperplane, but it needs to be bigger than 1, because points in the negative class will be always will be negative, and it is a negative class, so if you multiply negative by negative, you'll get a positive, and it needs to be behind the line, so it will be equal to 1 or more. And for positive is positive number multiplied by positive number, so it will be also more than 1. So let me write the equation. So it will be the y label, so the label of the class, the -1 or 1. So before the condition, I need to make a for loop for index index of our data and the input features of that data on that index. We'll enumerate self.x, so it will divide the x into the index and the input features. I will define the condition of the hinge loss function, so the y label index, so our predicted y label, the -1 or y, the -1 or 1 times np dot function in Python is a scalar compaction, so it is a multiplication of two vectors or metrics. So I will multiply the input features with the weight vector, and I will divide from that the bias, and this needs to be more or equal to 1. If condition equal to true, so the point is correctly classified. Point is correctly classified. Then we will make a little adjustment. All this function that is updating our line is using gradient descent. That means we are using partial derivatives. So if we derivate this function by the weight vector, we will got how much depends that whole function on that one parameter. The hinge function is like, can be like waves or anything else, but you need to find the global minimum, and the derivation is the slope of that minus, and you are giving the weight, like moving the weight like to the more positive values. You need to, the slope is minus, you need to add the weight if it's positive, and you are still moving the weight to the more positive values. You need to subtract the weight to get closer to the global minimum. And also the same applies for the bias. Let me write the code, because this is like, as I said, this is not that easy to explain. 2 times 12 lambda parameter. It is just a regulation, so the big points won't move the line too much, and it won't overfit on every outlier. Times self dot weight vector, so you will move the weight vector like this, and the bias will be the same. Else a point is not correctly classified. That means we will make not different adjustments to the final equation. So dv will be equal to the same regulation parameter 2 times the regulation parameter times the self weight, but also minus the multiplication of two vectors, the xy, not like this, the input features, and the y label. Index, our y label. And the bias will be the label of our index, the label of our data. And after this, we need to update our weight vector and the bias. So self.weight is equal to self.weight minus, so as I said, we need to go the opposite way to find the global minimum. So So that means minus learning rate, not the learning rate, but the object learning rate. So we don't need to jump from one side to other, but one point will, and one iteration will move slightly to the global minimum. Self-learning rate is multiplied by the derivation by the weight vector, and also for the bias, self.bias minus self.learning rate multiplied by the derivation of bias, derivation to the respect of bias. There is a mistake. I put here 2 underscores, but there is only one. The last method of this function is for predicting. That's the important finish. So I will put the object itself and also the input features. Based of them we will predict the result. So output will be np.dot, the x, the multiplication of the x vector will be the weight vector minus the bias, minus the object bias. This and the predict, it will give us value, but we want to predict only the +1 class with the name +1 and the -1 class. If it gives us the value 224, it will still be the +1 class. So the predicted label we will put there, I will call it predicted labels, will be numpy, that sign, only the sign of the result. And the result is called output. In our dataset there is 0 for the not bought car, so I will only change the y-hat will be the final prediction, and I will use the I will use the numpy function where, so where predicted label is less or equal to -1, there will be not. That means the customer didn't buy a car, that means, and the one for the customers, that others that bought a car. And I will return this y-hat. There is missing column. Our method is done. Let me make a quick recap. We divided the dataset, then we write a classification class from the SVM. There is initialization of our input features, the feed method, so the learning method for our classifier. This is one iteration, how it works, and this function predict the result based on the iterations. Before predicting any values, we need to standardize the input features in order to have the same impact of every feature. That means import from sklearn, preprocessing, import standard scalar. So scalar will be instance of that class, and train will be equal to scalar dot fit, also training the scalar on the x train, and I will also transform the x train, and I will also transform the x test, the scalar, but I won't train the scalar also on the x test because we need unknown data. Okay? So transform x test. Now that's all. So after this we can train our classifier from this classification function. So classifier will be equal to the instance of our SVM classification function. I will copy this, paste it here. Learning rate will be 0.01 and the number of iterations will be 10,000. This, and the lambda parameter will be, in our case, I don't know, 0.01. This is just suitable values for our classification class. You will get it by doing hands-on programs. So we initialize our classifier and now we need to train it. Classifier dot fit, put here the X train and the Y train. Yeah, like this. And now we can predict value. So classifier, we will print it out. So print classifier dot predict color dot transform, and you need to put here like this bracket, also double square brackets because it is a convention. We will take, for example, this guy with 35 years and estimated salary of 20,000. I will put him here and run the code. I hope everything will be working, but it is not. Yeah, I know what is wrong. You cannot put the prediction here. It expects only the 2 input variable. But something is also wrong. So the mistake, I find it. Our weights are not numpy array. It is numpy array, but it is numpy array of zeros, because numpy array will create empty numpy array, and these zeros will be creating the numpy array of number of zeros that is equal to the number of columns. So run the code again, and now it should be working. As you can see, the 0 is here, and for this guy, he didn't bought a car, and our model predicted that he didn't bought a car. I will make a prediction for all the other data. For this, I will need to import another library from sklearn metrics, import accuracy score, and now our predicted y, the array of our predictions, of all the predictions, will be the classifier predict the X test. So there will be the prediction of every row of our X test, and we need to somehow print it out that will make sense. So test data accuracy will be equal to accuracy score between the Y test and Y, our predicted Y, and the real Y. After this, I will print out through the F string. This is the accuracy of our model. This, and print out the test data accuracy. And the last column, I will print out the columns like next to each other. The first one will be our prediction, and the second one will be the real values. I will do it with the concatenate function from the numpy, like this, y prediction, and I will reshape it to make it from this to vertical. Y prediction, and here put 1, and I will reshape, I will concatenate it with the y test dot reshape, the same, reshape the y test, I think I need here a comma, and also this one, and the last one will be also flip everything like this. I'm missing one, I need to reshape it, but the reshape takes the number of rows and number of columns, so but I don't need, I need to the length of this, and also the length here and here. So like this, it's not correct. Like the length of this is the parenthesis for this. Why reshape? We found this, and we are missing one bracket. Like this is for this, concatenating together, and here is the last parenthesis. I fix it. I have some parentheses issues. I fixed the missing parentheses. Now I can make the prediction for all our data. Run the code, and you see the accuracy of our model is 88%, and the first column is our predicted labels, and the second one is the correct labels from the dataset. Yeah, they are pretty similar. You can use this code as a template for your future projects. It will work. Just rename this one line and change this based on the input data, or you can tweak the code and make your own project. You will learn much more. Thank you for watching. I hope you enjoyed the tutorial. Smash the like button, hit subscribe, and have a nice day. Peace.